Hi. Hi, everyone. Welcome and good evening. My name is Melissa Franklin, and on behalf of Harvard University, Division of Science, Harvard Library, and the Harvard Bookstore, I'd like to welcome you to the latest installment of our Harvard Science Book Talk series. I'm thrilled to introduce this event with Bob Cahn and Chris Quigg, who are presenting their new book, Grace in All Simplicity. Our event tonight consists of 40 minutes of discussion about the book and then 20 minutes of questions from the audience. So please ask a question, put it in the questions, and we will get to them. I want to also thank our partners from the Harvard Bookstore. It's an independent bookstore. And for all of you for showing up tonight in support of publishers, authors, bookstores, and of course for science. So it's my pleasure to introduce our speakers. These are two people that I know very well. I first met Bob Cahn when I was a graduate student at Stanford. I got to know him better when I was a postdoc at LBL, where he was a senior scientist. Then I got to know him even better by reading his wonderful book, which I used to teach. And it's called The Experimental Foundations of Particle Physics. It's really which he wrote with Gerson Goldhaber. And it has all the basic papers of particle physics, all the discovery papers. But then I really didn't get to know him until I read his bio that he sent for this book. And after I read the bio, I took a deep breath and I remembered that you're not supposed to compare yourself with anybody. So I now know who he is. So Bob Cahn is a Harvard grad, and he's from California, and he did his PhD at Berkeley with someone called J.D. Jackson, who I'll talk about. He's a particle theorist working on the Standard Model and has worked closely with experimentalists in the last 30 years of his life. He was one of the first to think about interesting ways in which you can create a massive Higgs boson at a proton collider. He's the author of 792 papers, which is a ridiculous amount of papers for a theorist, but he joined experiments so that he was on the Babar experiment at Stanford, and he was on an astrophysics experiment at LBL, the Lawrence Berkeley lab. He's really just too impressive to go on and on with this. So I'll just go on and talk about Chris Quigg. I should say he also had a role as director of the physics division of LBL. And in that role, he had a lot of interesting excitement that comes out in the book. I first met Chris Quigg when I was about 16. I was working at Fermilab, which is a lab just outside of Chicago for the summer, and was walking around one day with nothing to do. And I saw a door open, and I took that to mean come in and ask a question. Chris has been a friend ever since. Well, more like someone just looking out for me and teaching me things and telling me how to do stuff. Chris was an undergrad at Yale and then a Berkeley graduate student with J.D. Jackson. So the link between these two authors are a PhD advisor. He has been a career senior scientist or distinguished senior scientist and head of the theory group for some time at Fermilab outside Chicago. Chris also made an estimate of the upper limit of the Higgs mass long before it was found, before we found it. And it's not wrong. He's a little off from what the actual value is, but he also is very famous for being the Q in something called the ELHQ, which was a theoretical collaboration. Basically, it was a book-length paper about supercollider physics. He's also incredibly good at giving public lectures, and he just recently wrote an article about how to give a public lecture, which I have used. I also have to say that I steal from Chris all the time metaphors, but I think that's okay because Coleridge also stole metaphors from scientists at the Royal Society, so I think it's good. About this book, did I show you the book? There it is, Grace in All Simplicity. My colleague, David Salzberg, who was the physics advisor to the TV show The Big Bang Theory, says, it's erudite but accessible. Grace interweaves scientific adventure with remarkable human stories. Grace is also personal, as the authors themselves participated in and were affected by many of these great discoveries. This makes the book a fine embarkation for those just beginning their journey, for those already on a scientific path, and for anyone who has followed this great story. So please welcome them now, Bob Cahn and Chris Quigg.
Hello, Melissa. Hello, everyone.
Thanks for the intro, Melissa. Very kind.
Okay, so I have a first question, which is, you were both graduate students of someone called J.D. Jackson, a Canadian person who wrote a very, very famous textbook, graduate textbook on electromagnetism. And most people are scarred for life by having taken a course with J.D. Jackson and having to do the problems, and yet you two somehow made it through and also somehow stayed with him. I mean, that is, you were not scarred, apparently. So I just wondered if you wanted to say.
Well, we could show the stigmata, but it would be wrong.
The stigmata. Here's the book.
That's the third edition of the book.
Third
yes.
edition.
Yeah.
So we started with the first edition and lived through the second edition. Luckily for me, so he's a wonderful man, full of warmth, like all Canadians, and a true scholar. Luckily for me, because I was his student, no one ever asked me to teach electrodynamics because they thought it would mark the students too badly.
Did you, Chris? Did you ever take the course from Dave? I don't think so.
No.
No, neither of us took that famous course. We took particle physics from Dave, and that's what, at least in my case, seduced me into the field. I had started out doing condensed matter physics, but after taking Dave's particle physics course, I left condensed matter physics once and for all.
I should say that Chris says he's never taught electromagnetism, but in fact, he wrote a book called Gauge Theories of the Strong, Weak, and Electromagnetic Interaction. So,
Dave's book was about classical electrodynamics.
Yeah, I know. It was about classical electrodynamics. So, okay, so this book is kind of interesting to me. I started to read it and I realized that it's quite nonlinear in time. And it covers sort of 1400 to now. And it has, and it goes back and forth. So it's kind of very, very interesting and not like any book I've actually read before. And I guess I have a few questions is what reader did you have in mind? And how did you stop yourself from going down too far in rabbit holes? Because what it looks like is you traveled the world, the two of you. I don't know if you both did, but it seems like the two of you traveled the world, going to every place where something interesting happened, and then told us a little bit about it and told us about what happened. But for me, I would end up going down some huge rabbit hole and getting stuck in the bottom. So did this book take 30 years to write, or did you just
35?
35?
35. Well, we started in 1988, and we were anxious to get it out quickly because we wanted it done before the super collider, the SSC, came online. And we succeeded in that, but not in the way we had anticipated. Since the SSC died in 1993, this gave us some extra time to work on the book. And we did finally complete it after something like 35 years. Not working continuously, but.
So, I mean, one of the things I noticed is that this book is really good for me. And I'm not me, so I can't tell if it's good for people who don't know physics, but it seems to describe physics in very simple terms, and it's not a tutorial. You know, for the physics professor in me, I always have to try and make a tutorial, but this seems to be just more a description, a really good description rather than explanation. I was wondering whether that's...
Well, from the beginning, we had in mind readers of the old New Yorker, perhaps the contemporary New Yorker, which is to say, curious people who are drawn to long-form nonfiction. And, you know, one of the things that all of us do in conversation, and the best essayists do, is to engage other people in topics they didn't know they had an interest in. So we worked hard to try to do that. And our method, to the extent that it was a method, is to start with ideas that are familiar to people that may be remote from particle physics themselves, and encourage people. So we think of it as a conversation, even though only one side is doing the talking. We want the readers to be talking back or talking to themselves, and to engage with ideas, and then use those to draw them into corresponding ideas in physics, particle physics, cosmology. So that was the dream for us.
And why do you say the old New Yorker? Sorry.
Well, the New Yorker went through its Vanity Fair period. I think the current New Yorker is terrific, and I would include that in our aspirations.
Okay. So one thing that I found really interesting, one thing I love, and which doesn't happen very often, is finding out what other physicists in your own field think about physics, like what they actually think when they think about a concept. And so writing a book like this is actually, you know, bearing your most intimate physics soul to the world. So I think it's very brave, but I also wonder whether, you know, you too, when talking about these things, would look at each other and say, "Are you kidding? That's what you think? That's what you think is happening here?" Or do you know what I mean? Was there that interplay?
I think the interplay was less about the physics, where we probably had fairly similar views, and maybe more about how to present things and questions of style. I mean, clearly one of the challenges here was to write for the lay audience. We're used to writing papers for our colleagues. And this was a very different sort of intellectual challenge, but one I think we both found attractive and interesting. Our writing styles have some similarities, and they have some differences, and so that made for plenty of discussion.
Well, I certainly found, I have to say, I found things that you guys wrote, things I hadn't heard before or thought of before. So I thought it was great. But that could just be me.
Well, no, there were things we hadn't thought about or heard about before also.
Okay. So one of the
let me just interject for a moment. One of the things that we found very difficult in the beginning was to include ourselves in the book, because we are trained, you will know this, and I'm sure you instill it in your students. When we write physics papers, you tend to make it totally objective and not to inject the personality of people. And it is a shortcoming of a few of our colleagues to be able to show themselves, but only by saying, "Look at me, look at me." So we wanted to be able to reveal ourselves without seeming to draw attention to ourselves, undue attention to ourselves. And that took some learning on the part of both of us as individuals and as a pair.
I think one of the interesting discoveries in writing the book was to find that some of the personal recollections of our childhood were extremely similar. I mean, we grew up 2,000 miles, well, 3,000 miles away from each other, but Chris describes in the book his experiences discovering electricity and magnetism with a big dry cell. And I went through exactly the same experiences, bought exactly the same things, and did exactly the same experiments as Chris, you know, years before we knew each other. And then we discovered as well that we had both played this wonderful game called All-Star Baseball, which we discuss at some length in the book as a sort of sports-minded Monte Carlo. And we both were real enthusiasts of All-Star Baseball. In fact, Chris even found somewhere out on the web a place you could buy this game, and he sent me a copy. So I now once again have All-Star Baseball in my closet. So it was surprising to find out we had all of these common experiences growing up on opposite sides of the country well before we met.
Yeah. Okay, well, I have a couple of questions about the physics that I thought was kind of interesting. And one of the things you talk about is the symmetries underlying the universe. And you say that in architecture, for instance, we say that form follows function. So it's if you need to go upstairs, then the form is the staircase or the elevator. And then you say that in physics, that function follows form. That the form is the form of the symmetries, and the function is sort of the forces. So can you talk a little about that? Because I think it's an interesting idea. Someone?
Sure, I can start. Well, again, this is an example of trying to meet people in their prior experience. Many people have heard the slogan, form follows function, which dates to Louis Sullivan, the famous Chicago architect, who was famous for designing department stores and many other things. And he was rebelling against a neoclassical tradition in which every building had to look like a Roman bath or a Greek temple. So he's trying to overthrow this, and he made the point that you should know what the building is going to do. And just as a Roman bath served the function of people bathing, your building should not emulate people bathing, but should do whatever it's supposed to do. And there is a discovery that dates to Emmy Noether in 1918 that, and not recognized in its full power for decades, that symmetries underlie the interactions of the universe. So even gravity, but electromagnetism, the strong and weak interactions that we talk about in particle physics. And this was turned into a slogan by C.N. Yang and his followers, which was that symmetries beget interactions. So that discovering a symmetry in nature, observing a sameness, something that doesn't change, an outcome that doesn't change when you make changes into the appearance of something, actually leads us by a well-described path to derive the forces that govern the universe. And this was in my head, in our heads, and we realized that we could turn on its head the Louis Sullivan slogan and to change it into function follows form, which is, if you like, a paraphrase of the symmetries beget interactions.
I think that one of the things that's interesting about this particular example is that there's another, I think it illustrates another fact that we encountered along the way. So Emmy Noether comes up with these theorems, as Chris says, back in the early 20th century, which are then widely ignored. I mean, she became an extremely famous mathematician for work in other areas, in algebra. But she developed these theorems, which now underlie a major part of particle physics. They're sort of rediscovered in a particular form by Yang and Mills, and applied in what you would say now is the wrong way. So first it's ignored, then it's rediscovered and used in the wrong way, but then in the end it turns out to be the answer to everything. So I think that that's kind of an interesting example of how ideas don't progress in a simple linear fashion in science.
This is quite important, and it's why we have memories and libraries, that many good ideas don't actually work for the problem to which they were first addressed. But the ideas, if they're good, and we can remember them, I think there's a contrast with biological evolution, which I will now prove that I don't understand. which is that when nature does a biological experiment and it dies out, that line dies out, it's gone forever until maybe some random process recreates it. But our ideas don't have to die. They can be remembered and they can be applied in new places. And there are many examples, large and small, of this phenomenon, certainly in theoretical physics, but I suspect also in instrumentation and the way we do experiments.
Well, you have a number of stories of people who were ignored, who might not have been ignored. There was one about some young man in maybe Wheaton, Illinois, an engineer who probably could have discovered the cosmic microwave background a lot earlier if someone had listened to him.
Well, that requires enormous improvements in instrumentation. What he did do, this is a man named Grote Reber, whose mother, by the way, was the elementary school teacher of Edwin Hubble, who is credited with discovering the expansion of the universe. Grote Reber was intrigued by Jansky's first observation that some radio signals were coming from out there. And he built in his mother's side yard, about a mile from where I'm sitting now, a big parabolic antenna which he could steer. And at a crude level, he was the first to do radio astronomy, that is to discover not the diffuse source of the cosmic microwave background, that came later in other hands, but to discover independent sources, what we would now see as point sources or extended sources. He visited Fermilab at one point after he had taken himself off to Tasmania. He was a pretty quirky character. And one of our reviews talks about the quirky characters. He might have been the quirkiest of the people that we identify, but he did this great stuff as a backyard astronomer. Bob and I, maybe you too, had neighbors who had telescopes and, reflecting telescopes or something. And that was sort of the gateway drug for us into science. I wonder if it happened that way for you as well.
No, I lived in a ghetto of art and letters. I don't think anybody had a telescope anywhere near me. There was a coin collector next door. That's about it. And then in following this story, there was another guy, Jansky, who actually also started looking at the sky from Bell Labs and seeing something interesting. I seem to remember that if you imagine you just have noise coming from somewhere, then you think, well, it can't be from anywhere in particular. And somehow he noticed that all the noise seemed to be coming from the Milky Way. Yeah, I hope I remember this correctly. And then they just said, yeah, okay, that's not interesting. Is that they stopped funding that particular thing.
They were concerned with not having too much static to interfere with radio telephone communication between the US and Europe. And Jansky's work, although to us it's fascinating and it's inspired Reber, was sufficient to say it's not such a problem. The quality of the calls will be enough that people will pay for them. And so Bell Labs checked that off and then returned to the subject much later to great effect.
So there's actually one of the things that's interesting about your book is that, it seems to go backward and forward in time, but it seems to go backward and forward in time in kind of loops, so that you actually have to go backward about any particular topic to go forward. And then so that the book is somehow not linear in time, but doesn't feel also that it's jangling around. It feels like it's got some purpose, that you're sort of as if you're connecting different pieces in a puzzle, that you have to go backward in time and into different places in space in order to do that. I kept thinking as I was reading the book, what would that map look like if I could map out it like as a world line, your book but I didn't actually do it.
I mean, I think one way to think of our book is sort of a tour guide. I mean, you might go on a tour of some country, some locale, and you go around and see all the sites, and you might be interested, say, in the history, the archaeology, but you don't take it chronologically because, you know, you run into these sites and they don't line up chronologically. You take them as they come. And so you might think of our book as a sort of a guidebook to the development of fundamental theories of particles and cosmology. But like other tour books, it's not completely chronological. We take things as they come, and there are little side trips that are interesting and turn out to be important later on. But it's not linear. If we can
And
use
and
that
it doesn't
phrase.
have pictures. A guidebook.
Yes, well, that's, yeah, some of my friends who've been reading the book said, well, wouldn't it have been easier for me if you'd given us some figures and things like that? But we had at the outset decided that there would be no diagrams, no figures, no photos. It was just going to be words. Nothing prevents you from drawing your own diagrams if you feel like it. And that's probably more worthwhile than having us give them to you. But we felt that was a ground rule that we wanted to insist upon. It was a book to read, but
I think I think it's good. I think that if you look at the writing, it's very, very clear. So you don't actually need a picture. I just meant as a guidebook. Usually there's a picture. So I have something else I want to talk about, which is something about becomes very clear in the book. At some point you talk about the scientist called Eddington, who was an early explicator of and a scientist, an astrophysicist. And you say he was a speculator rather than a predictor. And I remember that in Ernest Rutherford's lab, in the guy who saw that there was a nucleus in the atom, that he wouldn't let anybody in his lab speculate. If they were going to speculate, they had to leave the lab and go outside, which I thought was really, really interesting. And I also noticed that in your book, you don't talk a lot about speculative things like string theory, which I think you mention in one line, and, you know, the multiverse in another line. And I'm just wondering what your views on speculation versus prediction are. Oh, I mean, there are many books about string theory, so.
Sure, including good books.
Yeah.
We had a big story to tell, and we wanted to stick to it, I think is the best way to say that. We were trying to be coherent. We take our readers very seriously, take their capabilities seriously, and we didn't want to just have a list of all the buzzwords that one might have heard. But we tried in the last quarter or so of the book to give an idea of the open questions and the new ways of thinking that may be required to address them.
I think it's also the case, Melissa, as I think you know, that both Chris and I have always been very close to experiment in our research, and I think that also is reflected in the book. Much of the book, most of the book, is really about experimental discoveries. I mean, of course, there are great theoretical discoveries at some length that we expound on. Certainly, the Dirac equation being maybe the best example. But our own research has been very much oriented towards experimental work, and
Yeah, no,
that's a natural focus for us.
Yeah,
even though we're theorists.
Right. So theorists are sort of speculators sometimes, and
Yes.
also predictors. Yeah. No, okay. Good. So the other thing that came up with, I thought that I have not read about before, is the idea that there's a kind of Jekyll and Hyde thing going on in quantum mechanics, that you know, the oscillations of, for instance, neutrinos that you talk about in the book can be thought of as Jekyll and Hyde, Hyde-ish. So I wonder if you wanted.
Yeah,
I
well,
don't
I
know.
had fun with that idea when it came to me. I thought, as Chris said, we tried to start with things that people were familiar with outside of science and build on those. And in thinking, I wanted to do something about particle oscillations. And it occurred to me that maybe Dr. Jekyll and Mr. Hyde was a good thing, a good hook to hang it on. And I think it, for me at least, it worked. I mean, certainly particle oscillation is one of the most amazing aspects of quantum mechanics and particle physics. And there's some wonderful stories that go with it. It gave us a chance to talk also about Bruno Pontecorvo, who is one of the more amazing characters to show up in the book. And it gives us a chance to talk about his life, which is presented in a marvelous book by Frank Close called Half-Life. So yeah, this was another example of building on something that was more familiar. Particle oscillations is not familiar to the public the way perhaps at least the name Dr. Jekyll and Mr. Hyde is.
Yeah. So I'm not sure it's a metaphor, or I'm not sure what that is. But anyway, I'm always interested in stealing metaphors. But I recently realized that metaphors don't work completely. And so I was wondering in that one where it breaks down, but I thought it was very sweet. So I guess the other thing that I'm really interested in is something you talk about. You talk about the masses of the elementary particles, and you talk about mass in general, and what it is in a really, really nice way. I think I wrote down here somewhere how you described mass. You say, to an excellent approximation, the nucleon's mass arises from the relativistic energy stored up to confine the quarks into a tiny volume. So I'm just imagining the person who has to keep the quarks inside the bag, which is the nucleon, and having to do a lot of work. It's very simple and clear writing, and yet I wonder if it's true.
Beyond the shadow of a doubt, yes.
And I wonder, and also,
let me say that the point we were emphasizing there is that the old idea of mass before Einstein, so
yeah.
going back to Newton, was that it was the quantity of matter, and that the mass, if you put two things together, the mass of the two things together was the mass of the one plus the mass of the other. And in the case of the nucleon, it's not the sum of the constituents masses that matters. It is this wonderful, complicated phenomenon of holding them all in one place. And there's a further irony there. According to Einstein, the mass of an object is related to the inertia, which is the mass, is related to the energy of an object at rest. So a proton at rest has a certain mass. And the slight irony is that that object at rest is made up of lots of guys running around inside. And so they're in motion. Well, there was no way for Einstein to know that at the time, and it doesn't contradict his insight, but it shows that metaphors change over time as we learn more.
Yes. And the other thing that was interesting about this is you go on to talk about how we would calculate the mass of a proton. I think you do. And you talk about something called lattice QCD, or lattice. You do it a calculation on a lattice, meaning that you do it on a grid in space-time. And can you just talk about that a little? Because I think it's not so clear to most people. If you are able to calculate it in that way, in some way, which I hope you'll describe, why does it matter? What's the prize you get? I mean, it's obviously interesting, but what would it mean? You're not, no one wants to take this
No,
one.
let me start, but I'm going to hand it off to Chris. Let him do the hard part. So we have a theory of the strong interactions with a fancy name, quantum chromodynamics, and it's an analog of another theory we have called quantum electrodynamics, and that describes the interactions of charges and photons. And in that theory, we can calculate by doing a series of approximations. We do the main part of the interaction, and then we do a correction, and then we can do another correction, and so on. And we can do that because each correction is smaller than the previous one. But if we try to do that with quantum chromodynamics, it doesn't work. The corrections are bigger, not smaller. And so you have to find a completely different way to do the calculation. And I'll let Chris explain how you do it.
So it's even better or worse than that. One of the metaphors that we use in the book is to talk about a one-act play, a two-act play, a three-act play, and so on, corresponding to these different successive approximations ever closer to the truth that Bob was talking about. And the remarkable and very frustrating thing about this theory of the strong interactions, quantum chromodynamics, is that you could do an infinite number of such calculations and never learn that quarks and gluons are confined inside strongly interacting particles called hadrons. That is something that's not accessible to perturbation theory, as we call it. And so you have to solve the whole problem at once. And Ken Wilson, years ago, invented a technique for doing this by putting the calculation on a lattice, a space-time lattice, a grid. And it is then possible to actually do the whole so-called non-perturbative calculation. And people have made marvelous computational inventions, algorithmic inventions, and used a succession of larger and larger supercomputers to do this and give us real insights into how the mass comes about and what its value is.
So we'd be happy if
we have been jumping up and down, yes.
yes, we're happy. Okay, I have a few more questions. I got to the end of the book and I thought, okay, now it's going to wind down and they're not going to introduce any more new things. But just at the very end of the book, well, I thought you were winding down. You were imagining all possible universes. You discussed a little bit a game physicists play, which is, what if the world was slightly different? You know, what if the proton was had a smaller mass, had a larger mass than the neutron? What would happen? And then you say it's not a very fun game, but you would find that all the hydrogen in the world would go away within a few hours, and it would be really sad. We would all be dead. But you talk about playing this game, and you talk about what if there was a new symmetry called supersymmetry that half of the world of physics seems to believe there is, that for every spin 1/2 particles, there's a spin 1 particle. You say, well, what if it were true that it existed, but the super part, that we call them the normal particles and then the super particles, what if the super particles were lower mass than the particles? What would happen? It seemed very, very sad. But I want to know a little bit. You talk about playing this game, and you give it some great and fantastic examples, and then you talk about Leibniz and his theory of evil. I don't know. I put those together in my head, where Leibniz is imagining somehow, and I want you to tell me the story, what evil is, and how there could be a God that is an omniscient God that has an evil universe. And somehow Leibniz comes up with the same idea of imagining all possible universes, all possible worlds.
He got there before us. Yeah, he got there before us, yes.
Yes, he got there before. Yes. And the one thing when I went on a rabbit hole, I went down a rabbit hole to the Stanford Encyclopedia of Leibniz and about this. And as he's imagining all these universes or all these worlds, and he wants to think of the best possible world, he thinks of, oh, well, what's best? He says the best world is one that maximizes happiness of rational beings, or the best world is one that maximizes the quantity of essence. I don't know what that means. And then the best world, this is the best one. The best world is the one that yields the greatest variety of phenomenon governed by the simplest set of laws. So I was just wondering, this is 1600. Leibniz seems to be doing what we're doing in your idea of imagining all possible worlds.
So if Leibniz didn't exist, would Voltaire have had to invent him?
Yes. No, I'm just wondering, I mean, what's in this book is a lot of different people and their ideas, but this one seems kind of interesting.
Well, I gave a number of talks addressing this question and pointing out if we change some of these parameters, the terrible things that would happen, you know, that all the matter would disappear, or in the case of supersymmetry, everything would congeal into one mass. And after I finished the talk, which was at Princeton, David Gross came up to me and he said, well, you talked about all the terrible things that would happen if you made those kinds of changes. Are there any changes you can make that would make things better? Which I thought was a great response. And actually, I decided that while it was a good joke, it was also an interesting, serious question, and my answer was, well, no, in the sense that nature has evolved around, if we look just locally on the Earth, nature has evolved to deal with the circumstances that we have now. And if you started changing things just a little bit so it wasn't catastrophic, probably would still be catastrophic, because all living things had in fact evolved to deal with things as they are.
And
So,
David's comment goes back to Schopenhauer, who claimed this was the worst of all possible worlds, precisely because any little tinkering you did would make it fall apart.
mhm.
Now, these are assertions; they're not science, but they're interesting ideas to engage with.
So you in this book you talk about how theorists and experimentalists come together through simulation, through Monte Carlo simulation. We have these. You talk about the language of science, and part of it is Feynman diagrams, which describe particle interactions, and how theorists think about Feynman diagrams, and how experimentalists think about actually measuring particles. And then you say, well, how do we meet the theorists and experimentalists? And the idea, I think you're saying, is that you simulate your Feynman diagrams and we simulate our detectors, and we can talk to each other, which is a kind of amazing meeting place. Did I get that right?
Well, I think that's part of how we meet, but I think we meet in much more direct ways, and we talk to each other. We theorists, with you experimenters, we talk about physics and what the questions are and how we're going to go about addressing them. I think there is a lot of interactions. That's certainly what's made my life as a theorist especially interesting, was to be able to interact with not just with theorists, but with many experimenters, both in particle physics and in cosmology. There is a lot of interaction, I think. And I think, frankly, I think one of the problems that we're having in the field right now is that we're overdue for a big discovery. And I think theory becomes less interesting when we don't have experimental results that provide immediate challenges. I mean, sure, there are definitely some problems out there that we haven't solved, but it's much more stimulating when we have lots of things that we don't understand.
So can I ask one last question before we go to questions? One last Melissa question. What would you like to know? What big discovery would you like to have happen before you, for instance,
cease to do physics?
Cease to exist, yes. What is the thing you would really like would really be the happiest thing to find out?
That's easy.
Okay.
What's dark matter?
Okay.
That's a good question. I would like to complete our understanding of the Higgs boson and spontaneous electroweak symmetry breaking. I'd like to know that the Higgs boson does all the things we attribute to it, and in connection with the high energy behavior of the theory. And I would like to know where the mass of the electron really comes from and what sets its value.
Wow.
And I hope we get the answer before I forget the question.
Someone asked a question, someone asked a question saying, you wrote this book over 38 years. How did writing this book affect your doing physics? Like, how did it affect your interests or your understanding?
I don't know that it had a direct impact, but I think it had a real impact by broadening my interests in physics and quite generally in intellectual interests. I mean, I think it really did have an impact on me personally. It was, I think, a great thing to be participating in all those years. That was an intellectual endeavor that was quite distinct from the basic research that I was doing. And so it's an indirect effect on my research, but I think a direct effect on my intellectual life.
Yeah, I would say similar things, that there are certainly elements of, I wrote a book on gauge theories, which you flashed. And over the years, that's only the first edition. Over the years, in giving lots of summer school lectures and courses on these subjects, you try to come up with ways of making the ideas alive and intelligible to people beyond the arithmetic of the equations. And so some of that deep thinking about what's the real meaning of the theories has found its way into the book. The other thing that has affected me, I think, in a way that's not specific, is as we got to know, Bob and I have both had an interest in the foundations of our subject, the history of our subject forever. Finding that the people who did great things long ago were fallible and indefinite in the same way that we and our colleagues are, that they hesitate. It is often said that physicists and theorists in particular are very, how shall we say, self-confident, arrogant, maybe. But what you find when you really get to know us is that we're a bundle of contradictions, and that very frequently we do not take our ideas as seriously as nature takes them. And we came upon example after example of this in the heroes of the past. For example, Hubble wasn't so sure he had discovered the expansion of the universe. Zwicky had second thoughts about dark matter, and on and on. And, however quirky those people were, to find that they shared the same tentativeness that we strive for and that our best colleagues exhibit all the time was very interesting and reassuring.
And even theorists who were very sure of themselves sometimes didn't understand their own discoveries. I mean, there's a very nice discussion, I think, of Murray Gell-Mann refusing to believe that quarks were concrete entities. It was like the discussions that took place in the late 19th century when there were still chemists who said atoms are a really nice fiction, but they're not actually there. They're really good to calculate with, but they're not physical entities. And the same story repeated itself with quarks. And the most brilliant of the theorists, Murray, said, no, that the concrete quark model, that's for blockheads. So there are lots of contradictions there.
Yeah, but there's probably also a lot of cases where people found things that weren't true and people didn't believe them. So that you talk about that in the book also. There's a question here from Bill Bloomberg, which is, do you think that we will run out of available collision energy and accelerators on Earth and must turn to astrophysics to explore otherwise inaccessible realms of energy or smallness of dimension?
Well, astrophysics and cosmic ray physics are wonderful. They have the problem of producing very small numbers of collisions. And so in this era, the biggest question that they raise and address is, how are these particles being accelerated? Where are they coming from? And what does that tell us? I hope that we will continue to go to higher energies. Obviously, there are some limits, but there are proto-inventions, I would say, of accelerating techniques that might miniaturize at least the accelerator part of things dramatically. They're not going to come next week. I don't know whether they'll come within our lifetime, but I hope that people will continue to be inventive.
In the case of, let me come back to dark matter just for a moment. In the case of dark matter, we don't know exactly how to look for it, and we're looking for it both cosmologically and in accelerators, both.
Right. There's another question which is actually pretty interesting, which is, actually, it is interesting. The question is, why were you hoping that the completion of the book coincided with the completion of the SSC? What kind of expectations did you have for the SSC? So this is the super collider that was killed in its infancy in Texas. And I guess my question, I'm going to add to this question, which is, if the super collider had been built, and I know you were both you worked on this, both of you, we would now be at a different center of mass energy. And do you think we would have learned anything more if we had continued it?
We'd certainly be in a much better position, that's for sure. Not just for the present, we'd be in a much better position for the future as well.
Meaning,
I will tell you that I spent a lot of time at CERN, especially before the pandemic. And during one of my long visits, a former director general of CERN was also spending time there on sabbatical. And he used to come into my office to waste time. One day he came flying into my office and said, "Chris, I've been thinking, you should have built the SSC. It was the perfect machine." So I think this is an attitude that's widely held, that having that extra factor of 2.5 in energy would have given us the possibility of finding more things if they're there. The one thing that we knew that machine would do was to solve the mysteries of electroweak symmetry breaking, which turned out to be answered by the Higgs boson. And the LHC has been able to do that as well. We don't know what else is there, but it would have been very nice to have more headroom, as they say, and to explore the unknown.
so there are two questions. I'm going to ask them both. One is just, what's the title about? Well, what is the meaning of the title? And the second one, which is just, I'm just going to put it in your heads right now, because they're short questions, which is, how will artificial intelligence affect our research, or your research particularly?
Great. I'll take the easy one. So the title is lifted from The Phoenix and the Turtle by Shakespeare. How can you go wrong stealing from Shakespeare? There's a nice passage that says, "Beauty, truth, and rarity, grace in all simplicity," which has a very nice cadence to us. And beauty and truth are what we strive for. Rarity is a quality of some of the experimental searches that we conduct. And so that spoke to us. Bob can speak for himself. I think he was at first a little wary, and everybody is told you can make up whatever title you want because the editor isn't going to go for it. I think it grew on Bob over time, and our editor liked it. We didn't get rarity into the subtitle, but we got beauty and truth into the subtitle. So that's where that came from.
We should mention that beauty and truth were also words that were used to describe the last two quarks. B and T are also sometimes called beauty and truth. So there was that extra connection. And I think one of the themes of the book is that in the end, as you make more and more discoveries, surprisingly, the answers turn out to be simpler and simpler. And the picture that we have now of the fundamental interactions is so enormously simplified relative to the kind of thing that Chris and I were studying in 1968 or 1970. And that simplicity has come from experiments and from understanding them. And it's a very graceful history and resulted in real simplicity. On the AI subject, first of all, artificial intelligence is already, of course, being used, as you probably could describe better than Chris and I could, in analyzing experiments. I mean, all kinds of techniques are used to understand what's coming out of a very high energy collision. You train things, you have Monte Carlos, it's all a kind of artificial intelligence. And I would have been inclined to say, but it's not so obvious how to use it in theory. But then I was speaking to a colleague who does extraordinarily complicated sort of algebraic calculations, higher order QCD. And it turns out that there are people who are trying to use AI to sort of extrapolate from known answers, which have fantastic symmetries among them. What would be the next order? Actually using AI, which I thought was pretty amazing. So it not only has been a part of experiment for a long time, but it actually may be playing a role in theory.
I think they also use it in lattice QCD, but I could be wrong. There's one question which I like here. What do you think theorists and experimentalists, and this is from a young scientist, what do you think theorists and experimentalists should do to work together most effectively to move particle physics forward?
Spend time together, both in formal settings and in informal settings.
Make friends.
Yes, it's not happening a lot lately. It's on Zoom, maybe.
Well, on Zoom, there was the pandemic, and we still haven't recovered from that. Here at Fermilab, we still have a lot of experimenters who got in the habit of doing their analysis at home instead of coming to the laboratory. And that means that I don't get to see them, that their experimental colleagues don't get to see them. And, from your time at CERN, it's kind of a joke that everybody sits in the CERN cafeteria drinking coffee all day. And there's a certain amount of socializing and screwing around, but there's a great deal of the beginnings of scientific conversations that have enriched us enormously and give us a starting point. So I think spending time together and not just mailing papers or PDFs back and forth is essential.
I think that something can be done at the level of graduate school. I think that more exposure of the theorists to experiment, maybe even getting them into a lab, but certainly exposing them more to experiment and making sure that the experimenters also are exposed to theory. I think there really are things that can be done at the level of graduate school so that people have training that they can build on later. Both the theorists and the experimenters will have more mutual understanding, which I think is beneficial in the long run. In the case of cosmology, the distinction between experiment and theory is not nearly as sharp. And that's actually one of the very nice things about working in cosmology. Some people are more theoretical and some people are more working in hardware, but there's a middle ground where a lot of people are doing both. And that's actually very nice.
The last question. The big exciting news this week was when the particle physics world decided that they're going to support the idea of a muon collider, muons colliding on muons in the future, which is weird because muons only have a lifetime of 2 microseconds. So everyone is very excited about this. I'm just wondering do you wish you were going to be alive when it happened?
I don't think I want to be alive when I'm that old, frankly.
So you overstate slightly, Melissa. That it is the planning committee has endorsed that as a dream. while stating several times in the report, we don't know how to do this yet. But it would be very, very exciting to do. One of my enthusiastic young colleagues at a nearby institution, the University of Chicago, promises that this machine will come into operation on my 100th birthday. So she thinks that's good. I don't, not so sure.
I think that would be remarkably rapid.
Right. But it is a very, very, one of the things that we've done is to develop ways of more efficiently using the stable particles, the electron, proton, antiproton, anti-electron, and positron as projectiles. And a new frontier is to use unstable particles as these projectiles, which, as you correctly point out, means that you got to move really fast to get them to high energies. At high energies, their lifetimes are dilated by the effects of special relativity. And so it's not that you just have 2.2 microseconds to deal with them. You can stretch it out a bit, but not forever. It's a really interesting possibility, and it's a really tough technological challenge.
Okay, well, this was, first of all, I just want to say I loved this book. I really liked it. Not just because I like you guys, it was actually really good. And I loved having you. And I wish we had done it in person, but it's great having you by Zoom. And for everybody, for the audience, this has been recorded, and we will have it on the Harvard Bookstore website and the Division of Science website. So please, please tell people about it. And this was great. I'm very happy to have done this, and I'm even happier to have read the book. So on behalf of the Harvard University Division of Science, the Harvard Library, and the Harvard Bookstore, we wish you a great night. And we hope to see you at our next event.
Terrific. Thank you.
Thanks, Melissa.
And thanks to everybody who came, and to the bookstore. These bookstores and public libraries are the soul of our nation. So
support them.
Yeah, great. Okay.